Okay, I'd like to welcome you back. Appreciate everybody who's sticking around for this long week. Today, we are going to start out by talking about antimony functions again and how to integrate antimony with CompuCell. Last time, we only talked about antimony. We didn't talk about how to connect the two, although we used that connection. I need to remind you the workshop is live streamed, recorded, and distributed, so please be aware of that. I'm going to try to go through these examples today a little bit faster so that we have time to work on some more detailed understanding of how to integrate network models with CompuCell. And so we may skip some examples. You'll have the full slide deck and all of the exercise solutions are available to you through the student materials. They've also all been emailed to you. So today we're going to talk a little bit about some of the specific issues that you face when you're using antimony and some of its capabilities. There are a lot more. I recommend looking at the antimony cheat sheet and also their online material, which are very good. And then we will also begin to start doing integration. Please take the time now to launch NanoHub Jupyter Notebooks and the NanoHub CompuCell3D main tool, and also load into Twit in CompuCell the Tellurium v3 program that we used yesterday. You should still have that in your workspace. If not, please upload it again, because we're going to be continuing from where we left off yesterday. As I mentioned, you have always as a background Herbert's Systems Biology Introduction to Pathway Modeling book, which is great, the online documentation, and that Tellurium antimony cheat sheet, which are going to be very useful. We're only going to do a very limited fraction of the things that you can do with this kind of methodology. And I want to say that I hope it gives you a flavor for it, even if we can't do all of the things that one might want to do. To remind you from yesterday, antimony syntax is very simple. We take, in our Python, we're going to create a model string. We'll use triple quotes because the model string can have carriage returns in it. We remember that we can use double slash or hash as our marker for comments. A semicolon is the standard delimiter. Colon indicates a named rate law or a conditional. And we will define our models in the form of reactions, where we have the name of the reaction here, J1 colon, and then typically X being transformed into Y, semicolon, and the rate law for that transformation. We could write ODEs directly, T prime equals beta times T times V, semicolon. That would give us also dt by dt equals beta TV. We're going to talk a little bit about dynamic relationships in a minute, which are colon equals rather than equals. And so you're going to need to remember that level of syntax. If you have the example, you'll have it in front of you, and you can use that as a template going forward. I'll remind you also that if the model that you're working on has a format that you don't like, and we'll come back to this in a little bit, you could change the model step size, which is the time scale, and you can change the size of the image, and we'll come back and I'll show you the details there. I want to say a few words about antimony because it's what's called a declarative language. It is not a program. It is a specification of a model. And that means that it doesn't work quite the same way that a program does. In particular, with one exception, the order of the lines in your antimony string doesn't matter. If I write A equals 3, B equals 3, 5, A equals 10, then the A equals 10 overwrites the A equals 3. That's the only time that the order matters. Or if I said E1 equal colon T goes to I1, and then E1 colon something else, the second one will take precedence over the first. However, otherwise, the order in which I specify my lines doesn't matter, which is completely different from normal programs. I can say, I can define a value later on and have something depend on it before it. It's allowed. Another thing is that antimony itself is not, the string is not executed. The string is parsed and compiled and turned into executable code. And that means that particular equalities, assignments are only evaluated on loading. And that means that if I then change an assignment after a string has been loaded, it only affects the assignment value, that it doesn't change other things through assignments. And these are things that are typical of declarative languages, but may be unfamiliar if you're used to procedural languages. As we know, a language like Python or C++ has two kinds of equality. It'll have an assignment equality, and it'll also have a comparison equality. And we have to remember which one we're using in a particular context. And I like to joke, but it's also true, that Aristotle discussed this at the very beginning of his works in 350 BC. So this was something that's been known for a long time, that equality means different things in different contexts. Declarative languages have an additional kind of equality. In Antimony, the syntax is colon equals, and the difference between equals and colon equals is that it distinguishes when the assignment occurs. Equal sign is evaluated only when the model is loaded and parsed. Colon equals is dynamically updated. And that's going to be important because if I write a string that like this, that says C equals 3 times A, that will be evaluated on load, and A is 0, that will mean C is 0. But C will always be 0, even if A is a variable changes value. So that is something that you might not expect, because if you think of equal as an assignment, you have to remember that that assignment is only evaluated on load. So if I wrote, for example, a string K2 equals 3 times K1, K3 equals 3 times K2, K1 equals 2, notice this is an order that would not be legal in Python because I'm defining K1 after I've used it. This will happily produce K1 equals 2, K2 equals 6, K3 equals 8. If I then go and change, and I haven't actually shown you how to do this yet, we'll talk about this in a minute, the value of K1 in Python, K1 will change, but K2 and K3 will not. That's a little inconvenient if we want to have a scaling factor that propagates through our model. It's also going to be something that you might need to be aware of in a procedural language like Python. We can have a K3 times equals 3, or K3 equals 3 times K3. That's legal. That would update the value of K3. In a declarative language, this will generate an error because you're not allowed to have a recursive definition, because this can't be written in a way that the order doesn't matter. So you have to remember that this is, in fact, a different kind of thing from a program. Again, this colon equals, in fact, defines a continuous reevaluation. Again, the order doesn't matter. If I say K2 is equal to 3 times K1 with a colon equals, K3 colon equals 3 times K2, K1 equals 2. Now, if I change the value of K1 from Python, the values of K2 and K3 will update. So if I start out with K1 equals 2, K2 equals 6, K3 equals 18, now having used colon equals, if I change the value of K1, I'll get 10, 30, and 90. Notice that if I define K2 or K3 with a colon equals, I'm not allowed to change them from Python anymore. Those are now restricted in their use. And that means that you have to be a little bit creative when you use the colon equals notation. Okay, I hope people have had time to load our model from yesterday, that tellurium V3 model. I'll do that myself here. We want to go into Twit. We're going to open the tellurium V3 example, and we're going to work with that just a little bit. And I guess I overwrote the one that I wanted, so I'm going to have to change this. In the meantime, please, everybody, go back to the model. A goes to B, B goes to nothing. It rates K1A, K2B. Set K1 equal to 0.2, K2 equal to 1. Now I'll let you work on that. Sorry, I've got to screen share a different way now. I'll let you work on that while I'm going to do it as well. Okay, is the screen share working for people? Make sure everybody's seeing my split screen now. Is that right? Great, thank you. Okay, please load your tellurium V3. You shouldn't have it overwritten the way I do, because I was just doing that demo yesterday at the end. A goes to B at a rate K times A. B goes to nothing at a rate AB times B. Get rid of these lines that I'm not using. Again, if you're loading the one that I gave you, you wouldn't have to do this. You should have it already there. Change the value of Ka to 0.2. And I only have A and B, so I got to delete the display of the additional things. Make sure that that's right. If people have see a syntax error, you can correct me. I'd appreciate it. Let me run a quick poll to make sure that everybody has got that one done. This will be working with this model for a bit for today. I'm going to run it myself, just make sure that I didn't introduce a syntax error when I was running it. That tile function is always useful in the windows. And sure enough, it seems to work. Runs a little bit fast, so I'm going to run it, start it again. Just time step through it using the dot. Okay. Looks like everybody has that. All right. And now I want to use this concept of functional relationship. And there are a lot of ways that I could do that. Something that we could do would be to write that K1, instead of being 0.2, is 0.2 plus sine of t. And t, the reserved word for time in antimony, is time. And if we're going to have something change in time, we have to use colon equals. So I'd like you to try changing the K1 equals 0.2 to the K1 equals 0.2 plus sine of time using the colon equals notation. I'll do it with you. If you've already got it done, you could make K1 depend on a variable like A instead of on time. Antimony has basic mathematical functions. Exactly which ones are implemented, you'll have to look in the manuals, but sine is one that they have. And so I should probably give this a new name so I don't overwrite the one that I've been working with. Okay. Let me see if people have that working. And now, well, let's see, did it work? I didn't do it right, did I? What did I forget to do? What did I forget to do?
You didn't add a column?
I didn't add the column. It's easy to make that mistake. Okay, let's try it again. Now you'll see the value of A starts going up again because of that sinusoidal variation. Did everybody get that? Looks like people did. So that's pretty simple. Again, you can do a lot with this. It's a very powerful function. So you get something that looks like this. I'm drawing it here so it's a little clearer to see. You could do quite a bit more with that. The last thing I want to talk about with antimony syntax is events. Sometimes things change discontinuously in time. We can often do that in CompuCell through the Python layer, but you can do that in antimony itself. And again, the syntax is very simple. You name the event, E1 : and then you use the syntax at, and then a logical operation. For example, at time greater than 15, : there's an extra colon here, and then the thing that you want to have done, A = A + 15. In this case, notice it's not a : equals, because the event forces the evaluation of the thing on the right-hand side at the time the event becomes true. You can have multiple things depend on the same trigger. I could have A = A + 15, semicolon, B = B + 10, semicolon, C = C/2. Notice in this case, I am allowed to have A on both sides because it's something that's evaluated specifically at parse time. And so that may be a little bit unusual. I can't write A = A + 15 in the main program, but I can do it as an event. When the event goes from false to true, that's called a trigger. Time greater than 15 is always true. So you might expect this to add 15 and 15 and 15 and 15 and 15. Since that doesn't make any sense, this happens once whenever this argument goes from false to true. So again, the syntax is event name at logical expression, parameter name = expression, parameter name = expression. So why don't we try writing this, undo the change we just made to K2, and add the line E1 : at time greater than 15, A = A + 5. See what happens. I'm going to go back to my original K. And now I'm going to add an event. Where I do it doesn't matter. The indentation doesn't matter either. But I'll do it this way, E1 : at time greater than 15, : A = A + 5, semicolon. I'm going to save that. Everybody following that? Okay. Let me try that. A comes down. I get to my time 15 and my value of A goes up. Make sure everybody was able to get that to work. So here's our result. It only does it once, doesn't keep doing it. And that introduces the idea of a trigger. This event happens whenever the trigger goes from false to true. Now, in the case of time greater than 15, that only happens once. On the other hand, if I did something a little bit perverse, like sine of time greater than a half, that's going to happen every 2 pi units of time. So that would be a periodic trigger. The trigger has to go from true to false and then back to true. Whenever the trigger goes from false to true, this is executed. You can also do these things dependent not on time, but on a value. I could say if A is less than 1, make K1 change from plus K1 to minus K1. And so that's the one other thing that I'd like you to try. Write code so that when A is less than 1, K1 goes to minus K1. And again, when A is greater than 8, K1 goes to minus K1. So what happens when you do that? And what does that tell you about the way triggering works? So I'll do that with you, but I'd like everybody to do that as well. So again, at A less than 1, we're going to say that K1, or actually I said K1 here, but I called it KA. So please use the syntax that's correct for your model. KA equals minus KA. The second event, E2, at A greater than 8, KA equals minus KA. Maybe in the chat, somebody could tell me, either try this out or tell me what they think is going to happen. Is the screen share not working?
Yeah, it is.
Okay, thanks. So what's going to happen when I do this? Has everybody got it working? Has somebody done it?
A is oscillating.
They will oscillate, yes.
Yeah.
Why does that happen? If K1 is negative, what happens to this reaction? If K1 is positive, A is turning into B. If K1 is negative, what's happened?
It goes back up.
That's right. That's what a reverse reaction is. If I have a negative rate for A going to B, that means B goes to A. So if K1 is negative, A will increase. K1 is positive, A will decrease. So if A starts out big and K1 is positive, A decreases until it goes to be less than 1. K1 changes sign, so A will now increase. When A gets to 8, sign of K will go positive again, and A will start to decrease again. And so I will get a oscillatory result. Yeah, I've got a syntax error. Typo. I used a colon instead of a sentence. Did everybody get that? So you can use triggers and events to do rather complex programming, but you do have to think about things a little bit differently. It's not the same as procedural programming. It's much more like biology. Biology doesn't really have loops. Things happen simultaneously. There are triggers. If level of P53 goes above a threshold, cell dies. Well, those things happen. But triggering tends to happen in parallel. Doesn't care about the order, usually. Some things, of course, have to happen in succession, but there are lots of triggers waiting. And if any of those triggers happen, they happen. So you have to think about this as a sort of event-based programming. And it is a rather powerful thing to do. Again, we could do a lot of these things in the Python layer, but it's really more efficient and more natural. If there are properties of the cell that are changing, the cell should be doing the change. If you want us, for example, to have cell differentiate, this is a way for that to happen. If you want the cell to die under particular circumstances, this is a way for that to happen. So here's our result. I've noticed that there's some irregularities because I'm using a fairly big time step here. If I had a finer time step, it would be more uniform. So there are a lot of additional features of antimony that you could explore. You can define units, compartments, boundary species, many other things. We're not going to have time to do all of those today, but the basics I hope you've got now. So now I'd like to move on and talk about how you connect antimony with CompuCell. We've been ignoring all of that in this program, but it's there. The first thing to know is that when we load a antimony model, it's called an SBML model. And that's a little bit confusing. But all models, whatever language we start with, are going to be turned into what are called SBML models. Any variable or parameter that we specify in an SBML antimony model is available as a dictionary entry, our usual dictionary entry. There are going to be two kinds of model. We can have a global model, what's called a free-floating model, which is attached to the simulation as a whole. And we can have models that are attached to simulation objects, in particular cells. So each cell can have its own copy of a particular model. So the signaling network in one cell is different from the signaling network in another cell. Those are referenced as self.sbml. Model here is the name of the model. And we'll come back to that in a minute. And then, quote, variable name, quote, A. Cell.sbml model would be the same thing if we loaded that model into a cell. If I want to read the value of A, I would say A equals self.sbml.model of A. If I want to read the rate of a reaction, and I've named it J1, I can use self.sbml model, quote, J1. That's why naming reactions is useful. If I want to change the value, I say self.sbml model of Ka equals 10. Note you can't overwrite a rate. That's fixed. And if I use colon equals, I can't overwrite the name of the thing that's on the right. I mean, on the left of the colon equals either. I also can't overwrite, those are the main things. You have to play with that a little bit. Okay, it's a basic concept that you'll see. And if I look in my code here, and I know I don't like scrolling through code very much, but let's see. Here I have self.sbml model. Var is a dictionary entry name, a key. And so I'm using that in this code here. Okay. So again, to read the value of a variable, I say A or whatever name I like, equals self.spml model and the name of the variable. To assign it, self.spml model KA equals 10. So let's do that together. Let's go to line 31 in our code. I hope it's still line 31. That may have changed. It's not going to be line 31 anymore. I've changed my function a little bit. It'll now be line 26, not 31. And I want you to add a line that's going to change the value of KA here. Get rid of my conditionals, your conditional, because we're now going to change the value in Python rather than in Antimony. I want you to go in, and here in line, now it's 25, after I've loaded my model, I'm going to type, I have to remember what my variable name was, self.spml, and I named the string model, so that's how I use model, square bracket, quote, AA, is my rate for KA. Equals, and my value before was, I'm afraid I'm doing this slightly differently from what I have here. You can do the exercise as written if you like. KA was 0.2. Let's make KA 1.
Question?
Yes.
Yeah, so for CC3D, you know, Python, sometimes when you're writing a function, you start it, you press tab, and then the other features will come through. Do we have that same feature in CC3D?
You mean command completion? No. No, what you have instead are the twitted functions. So you have code snippets, but it's not automatic code completion.
Okay.
So if I do this here, and maybe I will just show you how to do this in the interest of time, since I don't think you want to write this whole model out. I've adjusted the value of KA here by hand. And if I now run this simulation, I will see that this behaves. Maybe I have to tile it so you can see it better. I will see that this now decays faster because that rate is higher than it was before. It's 5 times higher. And this is the basic syntax that we're going to use again and again in the simulation. If I don't remember my syntax, and I strongly recommend that people use code snippets, I go to CC3D Python, SBML solver, and I have to look through this menus because they're long. And I have add antimony model. I have copy SBML. I have delete model, get integrator, get simulator. Here I want, it's all the way at the bottom, near the bottom here, sorry. Get SBML value for free floating model. And that will give me the syntax, self.spml, whatever I called my model, and the name of my variable. So if you don't remember the syntax, look for it in those twitted directories. So instead of having pure command completion, that's what you get. Okay. I'm going to skip this exercise now, but you can do this together and play with changing initial values of A, B, and C, changing parameters. All be the same. Basically, everything that you have in the antimony is available through this dictionary just by using the key. The last thing that I wanted to talk to you about antimony with, I'm going to erase this now so that you have a clean code, is that antimony can also solve ordinary, yes, somebody says concentration can become negative. Yes, well, the particular rules that I wrote with sign for K1, where Ka was equal to 0.2 plus sine of T, that does allow the concentration to go negative. I wasn't trying to, that was just an example of mathematics. It wasn't actually biologically meaningful. Okay, the last thing I wanted to show you is that sometimes, as I mentioned, it doesn't make sense to talk about continuous variables. If you have very small numbers of molecular species, molecules interact stochastically, and the continuous approximation may not be a good one. CompuCell allows you to use the Gillespie algorithm, which is a stochastic solver for network models. One thing that you have to remember is that when you use Gillespie, the numerical value of your variables matters. The number 1 represents one molecule. Typically, when we scale things, we either scale them to a reference state so that our values go essentially between 0 and 1 compared to some reference concentration, or we'll do things in millimolar, nanomolar, so on. When we're doing Gillespie, we have to actually count individual molecules. So if you're in molar concentrations, you don't do Gillespie, because Gillespie also runs at a speed that goes down linearly with the number of molecules. So it's exceedingly slow if you have a large amount of molecules. However, there are times when it's important because those fluctuations can be significant. The other thing that you're going to find is that the step size is going to change as a function of the number of molecules. So you're going to have to do that. When we load our model, and I guess the slides are a tiny bit out of order here with this. When we load our model, our syntax is self.add free-floating antimony, and then we have the model, where our model comes from, the name the model will have in Python, and the step size. That converts antimony time units to CompuCell time units. 0.1 means that one antimony unit is 10 Monte Carlo steps. Step size of 10 would mean that one antimony time unit is 1/10 of a Monte Carlo step. So we can change our time scale. We can add the tag integrator equals Gillespie to do stochastic models. We can have ODEs and Gillespie models running in the same cell. We could load one model using Gillespie, one model using the ODE solvers. We can also have multiple models using using the ODE solvers with different rates. And somebody asked a highly technical question the other day about solvers. There are a number of other solvers that you can use. In general, it's not something you need to worry about unless you have problems with convergence. So the last thing that I would like to do here, and again, instead of going to this, well, let's do the whole model out. We're going to run out of time probably, but let's do it anyway. Why don't we actually do this exercise? Go and create a 4-state model. A goes to B, B goes to C, C goes to D, D goes to A. Rate constants all of 1. Initial value of A of 10. We'll have to add the variables here. And then in the line that loads the model, here it's line 24, add integrator equals Gillespie. And the one other thing you'll want to do is change the step size from 1 to 0.1 so you can see what's going on. Okay. So I'll give people a minute to do that. I'll do it with you. But is it clear what the question is? Are there any questions about that? Please feel free to ask. This is really just a demonstration of the Gillespie algorithm. Don't worry if you want to make sure that it doesn't crash, but if you use different parameter values or a slightly different model, it's not going to change the value of the exercise. As I say, if I were going to do this again, I probably would give you a simpler model so it didn't take quite as much time to type. And remember that while cut and paste doesn't work between this editor and the rest of your computer, it does work within the editor. So it can be pretty quick to change things around. So this is my basic model. A goes to B, B goes to C, C goes to D, D goes to A. Linear rates have to define A, B, C, and D rates, initial values, and I'll put in my other variables here. I spell orange right. Okay. And first I'm going to run this just as it is to make sure that I didn't introduce too many typos. I did something wrong.
I think you defined J2 twice.
Ah, yes, there we go. Thank you very much. Thank you. See, I make all the mistakes I warn you about, so thank you for catching. See if that works now. Yeah, that's working fine. I get equilibration to the same value, is what I expect. And now I want you to go in and in the place where I load the model, I'm going to do two things. I'm going to change the step size to 0.1, and I'm going to define the integrator equals Gillespie. Has everybody been able to get that to work? Let me make sure that people are able to get that to work. Looks like it works for people. Look what's happened. I have fluctuations, big fluctuations. Now, last thing. We started with A equals 10. Fluctuations go down like the square root of the number. So why don't you try A equals 1,000 and see what happens. So to do that, just go back here, make A equals 1,000, hit save, and now run it again. Notice that these curves are smooth, but there's still some random fluctuations. Did everybody get that? Okay. So now you can compare a stochastic to an ODE by changing one term. The one thing you will have to do is you'll have to adjust the step size. So here's an example. This was for A equals, let's see, 100 initially. Let me try 100 here. It's probably prettier than 1,000. 1,000, basically, there's no difference between the ODE and the stochastic model. For 100, for 10, the ODE and the stochastic model are totally different. The the stochastic model fluctuates everywhere. ODE is smooth. Here, you see, I approach the ODE model, but I have big fluctuations. And those fluctuations are very, very important when you do gene regulatory networks. It means, for example, that a toggle is not stable in reality. When it is stable as an ODE, you get fundamentally, qualitatively different results. If you want, as an extension, you could write your code so you plot both of these on top of each other to compare. You could write codes that runs the Gillespie model 10 times, overlays it, and you can then ask the question, does the Gillespie model average to the ODE? The answer is that a lot of times it does, but there are times when the Gillespie model will give you a qualitatively different answer. So no matter how many times you repeat it, you won't average to the ODE prediction. It means the ODE is predicting the wrong thing. And that's something to be aware of when you're thinking about model. This is the example when you go to plotting them on top of each other. So now I'd very quickly like to talk about how to integrate subcellular, multicellular, and diffusion models together. And we've seen examples of this before, some rather complex ones. There's some simpler ones like cell cycle model or circadian rhythm model. This is a model that I'd hoped to do, but we're not going to have time to do today, where you load a Tyson model, which is available online, into cells and have it control cell proliferation and division. We're going to talk in the next module about delta notch signaling and how to couple networks between cells. And the reason I want to rush a little bit now is because I want you to be able to get through that example in the next module. The key things that we have to do when we're going to integrate CompuCell and networks is first we have to specify the network. We can do that with Antimony, systems biology markup language, CellML, or MABOS. We have to load that network model either into the whole simulation or individual cells. We have to time step it. And that means we have to define the time relation between the models. We have to be able to read and write the variables and parameters, which you've seen how to do already. And then we're going to have to see how to couple variables between cells. And it's sometimes useful to be able to actually unload a model, to get rid of it, to delete it. CompuCell lets you load a free-floating model, lets you load a model into all cells, load into all cells of a particular cell by number of the cell, cell number 97. More usually, we load into a particular cell by cell reference. We can load a network into all cells of a given type. One type of cell might have a signaling mechanism that's not present in another, which is why we want to do that. And we've already seen free-floating models. The network itself could be specified in Antimony, the way we've done it. If you use SBML or some of these other language specifiers, you'll have to use a different editor to do it. So again, if we come back to our code, the first thing we have to do is specify our model. as a string. We can have multiple models with different string names. And we use the command add antimony model to cell to do loading into a particular cell. Model string equals the name of the model. Model name equals name, the cell, and the step size. So for example, here, and I think these are out of order now. Yes, these are out of order here. So one thing we might want to worry about is conversion factors. That step size here, we might want to define as a global variable. Days to MCS if our antimony model is written in days, seconds to MCS if our antimony model is written in seconds, and so on. To specify an antimony model string, we know how to do it here. I'm going to skip through this a little bit. If you're concerned about it, you can use twit to do that. Again, we define the string, which we've done here on the right. Our load functions, again, are add antimony model to cell. That loads into a single cell. The cell IDs loads it into cells with particular numbers. To cell types, with a list of cell types. Free-floating antimony model loads it into the background of the simulation. You're always going to have model string and the actual model specification, the name of the model you're going to use to reference it, and the step size. And you have some of the options we've seen, like integrator equals Gillespie. We could read the model from a file, in which case we give the path name of the file. Step size is the conversion of time units. And if you go to twit, you'll see lots of other options as well. One thing that we can do is we can specify the initial conditions in that load function. Let me put the load function up here. Here we've got self-add free-floating antimony. In that case, we can use initial conditions, either a dictionary reference like this, or initial conditions equals parentheses, curly brackets, and then a long list of initial condition specifications. I'm not going to work with that, but it's in the manuals if you want to learn how to do it. Remember that we have the code snippets, add free-floating antimony model under SBML solver. SBML solver, add antimony model, and so on. We have all of these options for adding models, time stepping models, copying them if we haven't talked about, deleting them, changing the integrator, getting the state of all of the variables, the individual values, and so on. And again, I'm not going to go through all the details here. Add free-floating antimony model. Remember that the twit code will paste in a lot of options. You'll usually have to delete some of those options for the code to work. The twit will paste in model file equals model file, model string equals model string. You can't have both. You either can specify the file source or the string that you're reading. You can't have both at once. So the code that you paste in, you have to edit before it'll work. Again, we have to worry about the name of the model, because we're going to use that repeatedly, and the step size. Once we've specified a model, we time step it. And the time stepping is all done with a single command, self.timestep_SBML. And that will time step all of our models together. Now, we don't have to specify time step all of our models at the same rate, because we can use that step size definition to specify how fast the model runs. We could load, if we loaded the same model in multiple cells, we could in fact give each one a different step size. I'm not sure what that would mean. Circadian clock runs faster in one cell than another. That would be allowed. And we can do, if we have convergence errors, one of the things that we can put in that load is an option that allows us to control our tolerances. I'm not going to go into that here, but we can specify the tolerances we allow if the models are particularly hard to solve numerically. Some hints on debugging. SPML models can crash, and they can crash for a number of reasons. Usually, it's because you have a rate law where there's somehow a divide by zero. I talked about syntax errors in Antimony, commenting things out and looking that way. Sometimes you'll have a reserved word, as I mentioned, that can cause a problem. But the most common reason that you'll have a crash of Antimony model is that you have a divide by zero. And that doesn't always give an informative result, error message. And so there are a couple of things that you need to do when you do that. The first one is to use that single step, time step, and ask the question, does it crash immediately? In which case you probably forgot to define a parameter value, and so that one of your rates has a divide by zero from the beginning. Or does it crash sometime into the simulation? And then look for divide by zeros or very, very large rates. If you have a divergent rate, you have to think carefully about whether biologically it really is divergent. There's something that happens very, very fast, or whether it's a mistake. If it does diverge really fast biologically, it's a pain computationally. And so you might ask the question, can you get away with smoothing it out and slowing it down a little bit to make it numerically easier? It's possible to change the step size during execution dynamically. It's not something that you want to do if you don't have to do it. Okay. I'm going to run out of time here. I was hoping to work with you to build a model together, but let's just walk through some of the ideas here. The step function is where you put the time stepping of your model. And so you're almost, whenever you're going to have an SPML or other kind of network model, you're going to see this call self.timestep_SPML. Only do that once. Make sure that it's not inside a loop. Don't put it inside a 4-cell loop, for example. Only do it once. Again, for reading and writing variables, if you've loaded a model into a cell, you reference cell.spml.modelName, variable name or parameter name. For a free-floating model, instead of cell dot, it's self dot. If I want to assign the value, I just put the same thing on the left of an equal sign, same cell dot, self dot. If I want to return a dictionary which has all of my values together, result equals self.spml.modelName.values will give me a big stack of all of the values in once. If I don't remember my syntax, use my twit SPML solver, get SPML value for free floating model, get SPML value, get SPML state. All of those are there. You'll have to put in, for where it says model, you'll have to put in the name you used. For variable, you'll have to put in the variable you used. So you'll have to edit. Boilerplate will be self.spml.modelName value name. That might be ODE model and T, and there's a missing parenthesis. We can copy and delete Antimony models. That is essentially cloning a model from one cell to another is possible. We can remove them or delete them from a cell if we need to. So I think it's probably worth doing trying to think about time here. We're going to have an opportunity to do more of this. I guess I'll ask a question. Would people like to do a very simple exercise using this technology now as a consolidation, or would you rather take a break and then come back and do a slightly more sophisticated exercise with this? I'll use the poll. If you would like to do a simple exercise now, say need more time. And if you would like to jump ahead and do a slightly more sophisticated exercise, say done. Looks like we have approximately an even vote between the two options, which was what I was afraid might happen. Let's see what we can do to do this together. I'll walk you through the exercise quickly, but I won't expect people to do it. I'll walk you through the steps. What I'd like people to do in this exercise, and you certainly can do it, is generate, we'll use Twidit to generate a basic simulation template with two kinds of cells proliferating quiescent, specify contact and volume constraints. CC3D ML will set target volume to 125. We'll build our little antimony model. Instead of A going to B and B going to nothing, we'll have B going back to A. We'll load the antimony model as a free-floating model, time step it, retrieve the data, and plot it. And I'm just going to walk you through the steps. So the first thing you want to do is create a basic simulation template. And you would do that by going to CC3D project, new project, and I would create template model, for example. And I remember I want a circle of cells. I'm going to use blob initializer here. I'm going to create two cell types, proliferating and quiescent. No chemical fields. I'm going to have contact energy. I'm going to have volume. And that's it. The next thing I'm going to do is set my target volume to be 125. So I go into my XML, my CC3D ML, change the target volumes to be 125. And I can save that. And I can run that. I get that. If you want to follow along, that's fine, but this is a review. The next thing I would do is define my antimony model. And I have my antimony model open in my other program, so I can cut and paste from it. I can go back here. I can grab my model. Use that as a template. And I can put that into the model that I'm working in. And I put that at the top of my simulation. Here I want A goes to B. B goes back to A. So I get rid of my excess code. I had different values of K here, 0.01, 0.025, A is 10, B is 0. And that's how I add the model. I now want to load it in. I go to my start function. And I go and I ask for CC3D Python, SBML solver, add free floating antimony model. Add free floating antimony model down here. Okay. I have to edit that string. I'm not using a model file, so I get rid of that. My model string was called model, so I have to edit that. I'll call my model name my model. And I'm going to have a step size of 1. And I'm not going to use any of the other options that it gives me. So I'm going to delete all of those extra options. In my step function, I have to step my simulation. Get rid of this loop. I don't need. My step function, I do self dot time step. I could get this from SBM, from the code, SBML. Open close parentheses. That's what I need to do there. And if I want to read my values, I'm going to skip doing the plotting because that'll take a little bit too much time. I want to do plotting. Remember, I go to start function. I go to CC3D Python, scientific plots, add, setup. Will give me my plotting ability. And then in my step function, I would go after my time step. I would go CC3D Python, scientific plots, add data points, add my data. If I don't remember how to reference my SBML model, okay, I don't remember how to reference my SBML model, I go to CC3D Python, SBML solver, get SBML value for free floating model. And that'll remind me of the syntax that I use. And I have to replace model name. I called my model my model. I have to remember whether I capitalized it or not. I didn't. And value would be the name of the variable. And I had A and B. So I do that. Okay. And if I run that, I can get a plot that looks like that. That's not a very exciting result, but you can do things like have a change of the value of A multiplying by 10 at a particular time. That's like an Antimony event. And you could do the same thing. Instead of loading a free-floating model, I could load the model into cells. You could do the same thing exactly that we had before. So you have these options, again, add antimony models to cell ID, cell types, cell, or free floating. Be nice to do a tracking field. One thing that we're going to do a lot is tracking fields. And the one thing that you're going to need to remember with tracking fields are initialized in the init after the stepable. I come down here, CC3D Python, extra fields, automatic tracking, track scalar attribute. I give the field a name. Here it would be A, attribute name A. And you might say, why doesn't that have the ability to directly display the SBML? It doesn't. So I would have to then create a dictionary entry to correspond to this for the cell. Cell.dict parenthesis quote A equals the value. So that's a standard syntax. That will then display inside each cell the value of that variable. I realized that that was a bit of a lightning review of that. We'll practice it in a few minutes in the next module. Again, I think everything that you need is going to be available to you in the CC3D Python. And the key thing is to have the printout of these options in front of you so that you can reference it. I'm going to call an end to the poll today. I'm going to do a completion poll now for the module. I understand that that may have gone by very fast for some people, and for some people it may have been slow because you've done it before. I hope it was a balance between the two. And we're going to come back at 11:30, and at 11:30 we will start working on actually building some simulations using these ideas. So please fill out the poll. If there are any questions, please feel free to ask now, and we'll go forward from there. Can I load to a cluster of cells? You mean if you have compartmental cells, you can load to, yes, you can load to them by ID or by cell handle. So please fill out the module poll and take a minute or two to do that, and then we'll come back and use some of these ideas to build a little bit of a more sophisticated model. And feel free to ask questions in the chat. Again, all of these examples, including the ones that were skipped, were emailed to you. So if you want to investigate the slide deck, you have that available to you. The examples that were skipped are available to you, and the code to implement all of the examples and problems is available to you. So you're welcome to go back and look at that in more detail offline. What's the purpose of the tracking function? Well, I would like to be able to know if I have, for example, a cell cycle protein, I'd like to be able to visualize what the level of that protein is in every cell. That'd be equivalent to doing something like a single cell immunostain. It's not very interesting if all the cells have the same value, but we're going to find that most of the time, if something interesting is happening, the models will be different in every cell. We need to have some way of seeing that. If we plotted the time series for each model in the 10,000 cells, we wouldn't be able to see what was going on. Good question. Okay, 2 minutes to go with the poll. Please do fill it out. Any other questions about that?
Professor, just to note that about adding options to the like antimony model that we want to apply for the cell. In the slide, I saw that you are saying if we say like an absolute or relative for tolerance, it's gonna work. But based on my experience, we should write absolute absolute underscore tolerance. In that case, it is applied to the model.
So there was a syntax error in the slide.
Yeah,
That's certainly possible. Thank you for catching that.
you're welcome.